Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of physics, which is nuclear reactions, fission and fusion. Nuclear reactions involve changes in the nucleus of an atom, leading to the release or absorption of energy. These reactions are fundamentally different from chemical reactions, which involve only the electrons surrounding the nucleus. There are two primary types of nuclear reactions, fission and fusion. Fission is the process in which a heavy nucleus splits into two or more smaller nuclei, releasing a significant amount of energy. This process occurs when a neutron strikes a heavy nucleus, making it unstable and causing it to break apart. Along with the smaller nuclei, additional neutrons and energy are released, which can trigger a chain reaction if not controlled. This principle is used in nuclear power plants, where controlled fission reactions generate electricity. However, in an uncontrolled state, as seen in nuclear weapons, fission can lead to devastating explosions. On the other hand, nuclear fusion is the process in which two light nuclei combine to form a heavier nucleus, releasing an even greater amount of energy. This reaction occurs under extremely high temperatures and pressures, allowing nuclei to overcome their natural repulsion and merge. Fusion is the primary energy source of the Sun and other stars, where hydrogen nuclei combine to form helium, producing immense energy that sustains life on Earth. Scientists are actively researching controlled fusion for energy production, as it promises a nearly limitless, clean, and sustainable power source. Despite both processes releasing energy, there are key differences between fission and fusion. Fission produces radioactive byproducts, requiring careful management and disposal, whereas fusion generates minimal waste, making it a cleaner alternative. Additionally, fission is easier to achieve under controlled conditions, which is why it is widely used in nuclear reactors, while fusion requires extreme conditions, making its practical implementation a significant scientific challenge. The applications of fission extend to nuclear power plants, where controlled chain reactions provide electricity to millions of homes. It is also used in medical treatments, such as radiation therapy for cancer. Fusion, though still under experimental research, has the potential to revolutionize energy production, offering a virtually endless supply of power without the risks associated with nuclear waste and reactor meltdowns. The energy released in fission reactions is harnessed in nuclear power plants to generate electricity. In a nuclear reactor, controlled fission reactions produce heat, which is then used to convert water into steam. This steam drives turbines that generate electricity. The efficiency of nuclear fission is significantly higher than that of conventional fossil fuels, making it an essential source of energy. However, nuclear fission also generates radioactive waste, which requires careful handling and disposal to prevent environmental and health hazards. Nuclear fission is also the principle behind atomic bombs, where an uncontrolled chain reaction leads to a massive release of energy, causing devastating explosions. The first use of nuclear weapons in warfare demonstrated the destructive potential of fission reactions, leading to ethical and geopolitical concerns about their proliferation. On the other hand, nuclear fusion is the process where two light atomic nuclei combine to form a heavier nucleus, releasing an immense amount of energy. This reaction powers the Sun and other stars, where hydrogen nuclei fuse under extremely high temperatures and pressures to form helium. The energy released from fusion sustains stellar processes and provides the light and heat necessary for life on Earth. Scientists have long sought to harness nuclear fusion for energy production, as it offers several advantages over fission. Fusion reactions produce significantly more energy than fission and generate minimal radioactive waste. Additionally, the primary fuel for fusion, isotopes of hydrogen such as deuterium and tritium, are abundant and widely available. However, achieving controlled nuclear fusion on Earth presents significant challenges. Fusion requires extremely high temperatures, millions of degrees Celsius, to overcome the electrostatic repulsion between positively charged nuclei. At these temperatures, matter exists in the plasma state, where atomic nuclei and electrons are separated. Magnetic confinement in devices like Tokamaks and inertial confinement using powerful lasers are two primary methods explored to achieve stable fusion reactions. Despite decades of research, practical nuclear fusion as an energy source remains an ongoing challenge, but advancements continue to bring us closer to this goal. One of the most well-known fusion reactions is the hydrogen bomb, which is significantly more powerful than atomic bombs based on fission. In a hydrogen bomb, a fission reaction is used to provide the extreme heat and pressure necessary to initiate fusion, resulting in an explosion of unprecedented magnitude. A crucial aspect of understanding nuclear reactions is Einstein's mass-energy equivalence principle, represented by the famous equation E is equal to mc2. This equation explains that a small amount of mass can be converted into a large amount of energy, which is the fundamental principle behind both fission and fusion reactions. The energy released in these processes originates from the binding energy that holds the nucleus together, and its conversion into usable energy is what makes nuclear reactions so powerful. The energy released in nuclear reactions comes from the conversion of a small amount of mass into energy, as described by Einstein's famous equation. This mass-to-energy conversion is what makes nuclear reactions much more powerful than chemical reactions, which only involve the rearrangement of atoms. Nuclear fission has been widely used in power generation, but it comes with challenges, including the disposal of radioactive waste and the risk of nuclear accidents. Fusion, on the other hand, holds promise as the ultimate energy source, but achieving the extremely high temperatures and pressures required for sustained fusion reactions remains a significant scientific and engineering challenge. Both fission and fusion have played a crucial role in technological advancements, from energy production to medical applications, space exploration, and national defense. Understanding these nuclear processes not only helps us harness their power responsibly, but also opens the door to future innovations in clean and sustainable energy. Thank you. This is AskPrep, your guide to mastering NEET preparation. Let's decode complex topics and simplify your journey to success.